Hello everyone, I'm Andrea Possemato and I'm a PhD student at Telecom. Today I'm going to present you the work I did in collaboration with Dario Nisi and Nick Fratantonio on preventing and detecting state inference attack on Android. So let's first see how state inference attack can be used to perform some phishing on Android. We start with the device of the victim infected with a banking Trojan. The banking Trojan wants to target the PayPal application. When the victim interacts with the PayPal application, in the background, the malware can understand that this event is going to occur. At the perfect time, the malware can show a malicious activity in order to steal information like the email and password. But how the malware is able to get that the PayPal application is going to be used by the victim? Actually, this information resides in mainly two layers on Android. The first one is a file system. There are several files like CMD line that can contain this information and can be abused by the malware. Luckily, this entire attack surface on file system has been fixed in Android 7. The second big layer of information that is abused by malware during the years is the Android system services. During several versions of Android, it was possible to find several vulnerable APIs. Google has fixed all the vulnerable API that it was aware of, but potentially there could still be more. For this paper, we wanted to tackle the problem of defeating state inference attack, and we researched in two complementary directions. The first one is prevention. We want to automatically identify vulnerable APIs. The second one is actually detection. We want to detect unknown vulnerable APIs on the device. Let's see first how we prevent state inference attack. Ideally, we would like to have a system that takes an input a generic API, it performs some operation, and then as output, we know if the API is not leaking anything interesting or if there is potential information leak. Let's now see how we implement this system in a very abstract way. We decided to use dynamic analysis. So we installed on our device several applications, amongst which PayPal. And we start with the target app not running. We take a generic API, we invoke it, and we store the return value. Then we perform several operations on the device, like we start the target application, we invoke the same API, and we store the return value. We perform this process several times by changing the type of interaction that we perform on the device. Once this process is done, we take all the data that we collected, we pass them to our analysis engine, and as output, we have that for this specific API, actually there might be a correlation between the change of the state and the return value. However, since we wanted to do all of this automatically, we have to face several challenges. The first one is that dynamic analysis is actually pretty slow, and we cannot analyze all the API. Since the API will still be a lot, we also have to find an automatic way to invoke them and also to automatically generate the argument and also to understand the semantic of the given argument. Last, we also have to automatically analyze all the results. We have to come up with a generic algorithm that can tell us if the API actually returns something interesting. Since the attack surface that we want to defeat is the Android system services, let's try to see how they work. Android system services actually really resemble how remote procedures call work. So if the application wants to use the activity manager, it has first to ask for a reference of the activity manager, then it can invoke an API. This API is then passed to a proxy object, and the proxy object simply procs the request to the binder device driver, and the binder device driver will actually forward everything to the remote component, in this case, the activity manager services. The proxy and the stub agrees on a common interface that defines all the methods that are exposed on the activity manager services. However, by analyzing this subcomponent of the Android system services, we realize that there might be some limitation. For example, if we just invoke the given API just directly from the manager, there is no guarantee that we control always all the argument of the function call. And also, we saw that before returning the return value to the caller, so to our application, the manager can actually perform some modification on the return value. For example, by removing sensitive information that can lead to state inference attack. What is also interesting to observe is that there is no guarantee that the manager wraps actually all the methods that are defined and available on the proxy. All these limitations target what was the previously fuzzed surface from previous work. And previous work completely missed an unknown attack surface defined on the proxy side. So we decided to perform our attack surface enumeration and take all the Android system services that are reachable from a third-party app. From these services, we extract a set of the API that are the candidate API that we're going to test. This API comes from the manager and from the proxy. At this stage, we perform some filtering just based on the return value and the arguments. For example, we discard an API if the return value is void and for which we cannot control any arguments. Since all this extraction phase is done at the source code, we can also extract the semantic for some arguments. For example, arguments named UID or PID or package name are actually providing some meaningful information that we can use. When we have to invoke the API, we perform it through reflection. Also, the argument creation is performed through reflection. We're able to automatically generate all the arguments and all the objects for a given API call. And when we encounter arguments for which we have a semantic, we actually define a specific value from a list of pre-computed values. Since we want to try to explore as much execution path as we can, we adopted two mutation strategy. The first one, we perform a complete iteration where we don't change any argument for a given API call. The second one is a complete iteration where we change arguments for each API call. This has the goal of trying to stimulate as much path as we can. And also, since we have to mimic the user behavior, we perform some automatic UI stimulation by performing several operations on the device, like starting the target app, for example, but not only. When the API is invoked, we have to collect the return value. And also we have to analyze and inspect it. We decided to flatten all the objects, no matter how complex they are, in order to have a dictionary representation, even for very complex objects. This is very helpful for the correlation phase, because we can check for each field if during the invocation the value changed in correspondence of a given action. And this way we can easily discard the value that never changed during the API invocation, the ones that are too stable, or on the other hand, the ones that change for every API invocation, the ones that are too noisy. When we identify that there is a potential correlation, we can perform a very quick validation because we know the API, we know the arguments that we used, we know the action to trigger, and we know also the potential field that we have to observe. The analysis framework looks like this. We start from the source code, we extract all the candidate API, and we perform the testing on the device. All the automation is performed on the device, and when we have the return value for the entire process, we pass all the results on the analysis engine, and the engine will tell us if the API is safe, so it is not interesting for us, or if it is interesting and there is a potential information leak. We executed our analysis framework on Android 8.1, 9, and 10. Let's see how Android 8.1 look like. From the extraction of the API, we identify 1,600 candidate API coming from both manager and from proxies. After the execution of the analysis pipeline on the device, just by removing the API with the constant return value or very noisy return value, we were able to reduce the candidate to 63 unique API. For these 63 API in Android 8.1, we were able to find the correlation and so potential vulnerable API for 21 of them. Please note that everything that comes from proxy since now was actually an unknown attack surface. We were also able to identify 6 API that were marked by Google as security vulnerabilities and for which we had CV. If you can see here, for the affected version, we don't have Android 10 because all the bugs were actually fixed. In total, on both Android 8.1 and 9, so we marked the 24 potential vulnerable API, but only 18 were leaking sensitive data. The other 12 API that are not listed as a security vulnerability is actually do leak some data, but won't fix by Google due to the type of permission that they are asking for. Let's now analyze the 6 false positives that we have. 2 APIs actually might still be used to mount a generic phishing attack, since the attacker can infer that one application is going to be used by the victim, but cannot infer which one. So we can just display a pop-up messages informing the user that an update is available. We will have the perfect timing, but we will not have any context. The remaining 4 API are actually real false positive, and we were not able to find any correlation for them. This concludes the part where we prevent state inference attack on the system. Let's now see how we detect them. As we see before, our tool combines both static and dynamic analysis, which potentially open our approach to false negative. So to protect the user from unknown vulnerabilities, we decide to study the feasibility of a runtime defense mechanism. The goal of this defense mechanism is to identify state inference attack at the moment they occur. We design our defense mechanism based on 2 key hypotheses, and we verify them to a series of experiments. The first hypothesis that we want to verify is that all the existing malware exploiting state inference attack actually implements polling behavior. To verify this hypothesis, we took several samples from all the well-known malware family on Android that are actually exploiting state inference attack to mount phishing. And we identified that all of these malware actually use several techniques to repeat a common task, which is the one of invoking the vulnerable API. What is interesting to see here is that all the malware polls at least with a delay that spans from 600 milliseconds to 1 second at maximum. And also that once they start this behavior, they never stop it. The second hypothesis that we want to verify is that benign applications rarely rely on polling. And when they do it, the nature of their behavior is actually different than the one exposed by malicious application. To verify this hypothesis, we created a data set of more than 10,000 applications. We divided this data set in a training set consisting of 20% of this application and the remaining 80% as a testing set. We then took the training set and we tried to analyze it to see if the hypothesis is actually verified. We took each application, we ran it for like 5 minutes, we log all the binder communication performed by a given application, and we flag all the API that are invoked at a rate of at least once every 2 seconds. And please note that this is twice as low as the minimum malware frequency rate that we recorded before, and for at least 60 seconds, since the malware does not stop the polling activities after they started it. What we observed from our result is that actually benign applications do perform polling, but the way they perform is actually slightly different from the malware. They only perform polling on the following categories of API. Everything that is related with video, so audio, video, and digital right management. We investigated all of these subsystems and we identified that none of these API can actually lead to state inference attack. So we can safely discard this API as in a whitelist for this moment. The second one is the bootstrap phase. We saw that benign applications do have a spike of their activity during a bootstrap time. So the first period of time where the application is executed. And we saw that the level of activity, and we measured this level as the frequency of the API invocation, decreased after the application transition from the bootstrap phase to the resting phase. And this means that they actually behave differently than malware. Based on this hypothesis, we designed our detection system. We modified the binder call to log every API call. Every time there is an API call that goes through the binder, we record the user ID that performed the API call, the timestamp, and the destination of this API call, so the services that was invoked. We raise an alert for applications that are performing API invocation at a rate of at least 1 invocation per 2 seconds for at least 60 seconds. Please note that this threshold is very conservative because it is half of the polling frequency that are used by real-world malware. Of course, malware can reduce the frequency of the polling behavior, but in order to avoid the detection. But since timing is actually a fundamental component for this attack, there will be a very visible delay between the launch of a legitimate application and the spoofed ones. We evaluate our detection system by analyzing the remaining part of the data set, the testing set. All of these applications were never analyzed before this point. And after a complete execution of 5 minutes of this 80% of the testing set, we raised the alert only for 39 applications. By looking carefully at them, we identified that there are several categories like crash analytics libraries, aggressive advertisement libraries, or application locker that they actually behave like malware. So it's very difficult to categorize them. The remaining 10 applications were actually just performing polling due to bad code practice. From a performance consideration, we performed some micro benchmarking, and we saw that in average, our detection system is responsible for an overhead of only 2% with respect to the baseline of the Android operating system. So to conclude, in this work, we showed how the Android platform is still affected by state inference attack. We systematically extended the attack surface, and we designed a new automatic framework that discovered 18 new vulnerable APIs. We characterized the polling behavior in malicious and benign application, uncovering differences that allow the proper classification. And to conclude, we leverage this finding to design and implement a new on-device detection mechanism that blocks the inference attack at the root. Thank you very much for your attention. If you have any questions, please feel free to ask. Thank you.